Right, so hello everybody. I'm Paul Fennell and I'm at Imperial, and I'm going to introduce David Danaci, who is also a researcher at Imperial. He completed his PhD at the University of Melbourne, and he has been working in CO2 separations for a long time. He does work at the moment in MOFs and other systems to basically separate CO2 out. So it's sort of high-tech, super adsorbents of the future. And
too much VAT to the story.
With that, I will let him get on with it. Right, go for it.
Thanks, Paul. Okay, good afternoon, everyone. Thank you for joining. We have everything there. Great. Okay. So as I'm sure you saw in the advertising, I'm going to be talking to you today about adsorbent screening for post-combustion capture via TSA. And this was kind of brought on by the significant focus that's been going on with materials development for CO2 capture. So we all see a number of publications on various, porous materials and adsorbents claiming that they are the next solution to everyone's problems. But the majority of these publications, or just in general, have little focus on kind of the cyclic performance. So how they would, in a representative environment, in industrial operation. So to help that, our aim is to develop an adsorbent screening tool. So this is somewhere in between rigorous modeling, which is the best kind of option, and simple isotherm analysis, which is the more popular approach at the moment. This TVSA work or TSA work is a follow-on from our previous work on PVSA that has been published. And I guess in general, overall, a couple of the things that we want to address are how do MOFs compare for large-scale post-combustion CO2 capture, and what improvements are necessary to increase the accessibility and reduce costs. Not necessarily for MOFs, but for also adsorption in general. So to do that, for this work, we developed a TVSA model, so temperature vacuum swing adsorption, and it's composed of these cyclic steps here. This is a general flowchart of the model. So in the first step of the model, the bed is saturated at the feed conditions. So if that's 4% CO2, at 40 degrees C, the adsorbent, the bed is assumed to be saturated at those conditions. The next two steps, so steps 2 and 3, is where the regeneration occurs, so the heating in this case. So the bed is heated in steps 2 and 3, and you have options for a blowdown step and the product collection step. So a blowdown step is essentially a purge of product. So you're venting the gas. And the purpose of this step is to kind of concentrate the CO2 product that you obtain in the product step here. 4% or 12% CO2, or even in the case of a cement post-combustion capture, 20% CO2, the majority of the gas is nitrogen. So the blowdown step can help you purge some of that nitrogen content. So you can choose to blow down some gas if you wish, and then you can collect your CO2 product at this step here. In the fourth step, we cool the bed from the regeneration temperature back to the adsorption temperature. This can be isochoric, so constant volume, or it can be isobaric, which is the case here. So we keep it isobaric because as the temperature reduces, the adsorbent will have a tendency to adsorb and reduce the pressure. So to counteract that, we feed in some gas to maintain the pressure. And then in the final step, this model is a shortcut model, and an assumption with this shortcut model is that from step 4, you want to kind of reset the bed back to step 1. And essentially that's what step 5 does. So you put in feed gas and you resaturate the bed to the feed conditions, or the conditions that it would be under step 1. And the vent is everything else that was in the bed previously. So this is the shockwave assumption, as it's called. So the feed comes in and displaces everything perfectly in the bed to then reset back to step 1. The assumptions that we have here is that this is an equilibrium model, which means the kinetics of adsorption are not accounted for, and that it's also well mixed, which means the composition is constant through the bed. There is no axial composition considered. So that the grand aim is that that TVSA model with your adsorbent properties and your operating conditions goes into then a process design model where you can size, enumerate, and cost your process equipment. Today, I'll be mostly focusing on the TSA model, and then there's 1 or 2 slides at the end talking about the economics. But this is still in progress. So the limitations of this kind of simple model are that the adsorption kinetics are not considered. So this makes it unsuitable for rigorous process design, as the mass transfer is not accounted for. And the kind of co-issue with that is that the adsorbent performance is generally overestimated in models like these. Another byproduct is that you are comparing adsorbents on the basis that equilibrium is achieved and that the adsorption kinetics are very fast. Most of the adsorbents that I'm going to show you today are very fast or fast. But if you want to use the model to compare a slow adsorbent to a fast adsorbent, there will be a greater disparity between what the model shows you and what is actually achievable. The benefits, however, is that you can get a representative cyclic performance evaluation in less than 5 seconds. This is much better than rigorous modeling, which is in the kind of tens of minutes mark. And that rapid evaluation can be coupled with process economics to then give you a screening tool or an adsorbent ranking that also accounts for the process design and economics aspect of the process. And I'll touch on that throughout some of the results as well. So kind of another problem that we face with this work is the limitation when it comes to input data. So there's definitely a lack of published isotherm data in the literature. So we found about 89 adsorbents, or around that mark, where experimental isotherms were reported in the literature. Then we had to fettle that down to 59, where more than 3 CO2 isotherms were reported. So we need isotherms at 3 temperatures because we need to account for the temperature effects of both the TSA and also the PSA or regular aspects of the adiabatic steps of the model as well. So then that 59 became 25 once we also wanted 3 nitrogen isotherms. In theory, you could get away with 2 each because that's the minimum amount you need to get a temperature effect and fit your Langmuir isotherm or your SIPS isotherm, whichever isotherm model you're using. But it's much less reliable. It's definitely preferred to have at least 3 and ideally more. Another thing that is lacking in the literature is heat capacity data. So when you're both working on TSA especially and also PSA, when you want to calculate the amount of energy you need to heat the bed, heat capacity data becomes quite important. And for most of the adsorbents here in this work, we've kind of assumed that most of the MOFs have the same heat capacity, just because that's the only data that was available. And the zeolites have the same heat capacity, and the activated carbons have the same heat capacity. So I guess this is just a message to, if there are any materials scientists out there listening, please measure more isotherms so we can evaluate adsorbents more efficiently. For TSA especially, energy consumption, or the calculation of energy consumption, is a factor to consider, because we have both a mechanical energy input from the feed gas blower or compressor and the vacuum pumps if you're employing vacuum, and also the thermal energy input to the bed for the regeneration. Which then kind of brings up the question, are all joules equal? I don't necessarily believe they are. Some joules are more valuable than others. So you need to come up with a way or employ a method to kind of have everything on the same basis. So the two common approaches are listed here. So the first approach is where you combine the thermal energy input and the mechanical energy input to obtain an equivalent work energy, or an equivalent mechanical energy. And you can do that by using the Carnot efficiency, by assuming that all of your thermal energy's potential is going to be utilized back down to the ambient temperature, and by applying an isentropic efficiency, by assuming there is some hypothetical turbine that can do this thermal energy conversion for you. So that way you can convert your heat energy to a mechanical work basis. The other alternative is to convert your mechanical work to a heat basis and have kind of the thermal energy equivalent. And this is the approach that I'll be using in these slides today. And this is where you say, well, this mechanical work is being provided by electricity, and then that electricity is derived from thermal energy, upstream. And then that has some kind of round trip efficiency, in this case, the power plant, to convert that thermal energy to electricity and then mechanical work. So this varies. You can have anywhere from kind of 30 to low 40s of a percent for this efficiency here, depending on your power plant technology. But I've assumed 1/3. So the mechanical work is penalized by a factor of 3 relative to thermal energy. And the reason why I've gone for this approach here today is because most people are kind of familiar with amine absorption and the regeneration energies associated with that, which is thermal energy. So the kind of specific energy values you see are on a thermal basis. So using the model and the approach described, we've had a look at 3 scenarios. So CO2 nitrogen mixtures. So there's no water, there's no impurities. From a natural gas-fired power station flue gas of 4.38% CO2, a coal-fired at 12.5%, and a cement plant with 21% CO2. We then kind of evaluate the adsorbents on 2 bases. So one is with fixed operating conditions. So one is with fixed operating conditions where the desorption is fixed at 200 degrees C. There is no blowdown used, and there is no vacuum used. So this is pure TSA from an adsorption temperature of 40 degrees C up to 200 degrees C. Then there's a little bit of work on variable operating conditions where we use a minimizer or an optimizer to select the desorption, blowdown, and vacuum conditions to give you a target purity and recovery. So here are the results for the adsorbent screening on the fixed conditions. I'll just run you through the plot. So the color of the points represents the CO2 purity. So orange and red and gray are the higher purity values. The size of the symbol represents the recovery. So the larger the symbol, the greater the recovery. And on the y-axis here, we have working capacity. So the working capacity is the number of moles of CO2 you obtain per kilogram of adsorbent over the whole cycle. In general, it can be said that a higher working capacity is more desirable because that minimizes the amount of adsorbent you need to capture a given amount of CO2, which then has the follow-on effect of, in theory, reducing your capital costs. The shape of the symbols, so the triangles represent the natural gas flue gas, the squares represent the coal-fired case, and the circles represent the cement case. Now, in general, we have an increasing trend across the cases. So the working capacity of the natural gas case is much lower than the cement case, which is expected due to the much higher concentration in the cement case. So you can adsorb more at higher concentrations. The standouts, I guess, are that the zeolite 13X, zeolite 5A, they demonstrate a very equivalent performance to UTSA 16, which is a MOF that seems to be demonstrating good performance for post-combustion capture applications in general. And what is very different to the last piece of work on PVSA is that the MOF 74s demonstrate quite excellent performance under TSA conditions. This is not unexpected, as they have a very high enthalpy of adsorption. So you would expect a change in temperature to cause a significant reduction in adsorption and hence good working capacity. These, and also I'll point out, this is a log axis on the y-axis. So the working capacity down here is quite poor. These kind of ZIF materials, and I guess these Dabco materials do not adsorb very strongly. So they have a very mild heat of adsorption. So for the lower concentration cases, they have a very small working capacity. And also temperature has a smaller effect on the adsorption capacity as well. So here is the same data set, but the specific energy reported on the y-axis. So the gigajoules of thermal energy you need to expend per ton of CO2 captured. Now, all of this middle section is quite atrocious, but that's really due to the very low working capacity because you obtain such a small amount of CO2 per cycle. Again, the better performing adsorbents in this case are the same as before because we have assumed that the heat capacities of all of these are equal. If you had actual heat capacity data, then you would also see the effect of adsorbent heat capacity on the specific energy. So down here we have, let's take the natural gas fired power plant example of 4% CO2. And for MG MOF 74, we're kind of in the 4-ish gigajoules thermal per ton of CO2. And with reasonably good purity and recovery. And for the 13X case, we're up in the kind of 8 gigajoules thermal per ton of CO2. 4 gigajoules per ton of CO2 is really very close to the MEA benchmark, but considering that there are more advanced absorbents out there now available at kind of the 3 gigajoules per ton of CO2 mark, then we haven't really achieved the claimed benefits of adsorption in this case, because TSA is always suggested as a potential alternative to chemical absorption, because you don't need to heat a large mass of liquid to do your regeneration and thus save energy. However, the working capacity is still not equivalent, and you also need to heat to a much higher temperature. So with some process kind of level optimizations or modifications, maybe it is possible to reduce. In theory, it is possible, but it is yet to be seen for this value to be reduced to the 2 gigajoules thermal per ton of CO2 case. So on the next slide, I've taken the natural gas case data for the TSA work that I've just shown you, and I've overlaid it with the PVSA work that we previously presented at the UKCCSRC and has been published. So the fixed operating conditions, so the 200 degrees C for TSA, and 1 kPa of vacuum for the PVSA case. And I'd like to highlight that this isn't really a fair comparison, right? Because each adsorbent is not really operating at their most ideal operating conditions. But I just wanted to show you this to highlight the importance of a combined adsorbent process design or selection. So we have the PVSA points as the squares and the TSA points as the circles, with the CO2 working capacity on the y-axis. It's generally assumed that TSA will give you a higher working capacity than PVSA, just because you're exploiting, one, the temperature, the kind of heat effects of adsorption, but also because with PVSA, it's adiabatic. So as you dissolve the gas, you have no control over the temperature in the vessel. So as it gets cooler, it wants to hold on to more gas. With TSA, on the other hand, you kind of eliminate that variable because you are supplying thermal energy and can overcome those limitations. But as you can see, there are very few adsorbents from this selection under these conditions where TSA is better or significantly better than PVSA. So up here in the zeolite area, and for the MOF 74s, TSA is indeed better in those cases under these conditions, but that's mostly due to their high heats of adsorption, where temperature has a big effect. In these kind of MOF cases where the heat of adsorption is very low, you don't gain significant benefit from TSA or TVSA. So this, as I mentioned just before, kind of highlights the need to select an adsorbent and a process, and ideally a cycle, for the exact separation that you're carrying out. So it's not fully accurate to say that UTSA 16 is worse than either of these, because they're very close, and with rigorous modeling, it may be possible to get equivalent performance out of those 5 adsorbents. It is, however, okay to say that there's a general ranking. So we can definitely say that these 5 will perform much better for this separation than the adsorbents down here. So now the question is, what if we want to target a particular purity and recovery? Because in the plots earlier, these were just whatever the resulting purity and recovery was. The US DOE set their lovely target of 95% purity and 90% recovery. So we're going to see what, if it's possible, under these conditions to obtain those kind of metrics for these adsorbents. And to do that, we're going to run an optimizer over these process conditions here while minimizing the energy consumption. So we're going to limit the desorption temperature to 250 degrees C. This is just as a temperature stability kind of measure, just in case there's thermal degradation issues with the MOFs. And we're going to allow the desorption pressure in step 3 to be anywhere between 1 kPa and the adsorption pressure. So TVSA up to just TSA. And we're going to allow no blowdown up to 95% blowdown. So this isn't the typical way to express blowdown. You would normally say you're blowing down to some pressure. But what this number represents is if it's 50%, then we're going to discard 50% of the gas that is collected during these steps. So we ran this for the 25 adsorbents for the natural gas case. And actually, many of the adsorbents could not achieve the target with this cycle over that temperature range. And the ones that could were the same 5 that showed the better performance in the last slides. In this slide, the orange colored circles are the points from the previous data, and the blue circles are the optimized conditions. We have energy on the y-axis, and working capacity is the size of the circle. So in the case of just taking MG-MOF74 as an example, the purity and recovery were not 95 and 90, they were lower. But apparently there is a combination of operating conditions where you can sacrifice some energy, so increase the energy consumption to then achieve those targets. And in this case, it's around 4.5 gigajoules per ton to achieve those targets. In the case of zeolite 13X, apparently we can achieve this target while consuming less energy per ton of CO2. And this kind of really highlights the importance of optimizing your process conditions. So the next few slides, I'm going to talk about the ideal adsorbent, or what isotherm properties are best to obtain the best performance for TSA. And the way we do this is we take the single site Langmuir isotherm, we fix the maximum capacity, right? Because we assume that CO2 and nitrogen will have the same saturation loading at infinite pressure. And then we vary the heats of adsorption for CO2 and nitrogen to generate a set of temperature-dependent isotherms. And then we run the model, in this case, under fixed conditions to generate a map. So some of you may have seen similar maps from the previous work. So we have the adsorbent capacity on the x-axis, the CO2 heat of adsorption on the y-axis, and the nitrogen heat of adsorption on the z-axis. These heats of adsorption are not necessarily meaningful absolute values, but it is just good to know that a higher heat of adsorption will give you a higher amount adsorbed and also a steeper isotherm. So in the natural gas case, gray is the 95+% area and red is the 90% plus purity area. There is a fairly large area where good results are obtained. And this is also the case for the recovery. As this is TSA, there's a very large region where good recovery is able to be obtained just as a result of using temperature to regenerate. The final plot here is the specific energy. So we kind of want the light blue and dark blue areas, what most people would be aiming for. And that really correlates with the CO2 purity. And that's just an artifact of this model, because the CO2 purity is directly linked to the working capacity, and the specific energy is also directly linked to the working capacity. What is interesting to see, up kind of in the extremely high CO2 enthalpies of adsorption, we suddenly end up in a very poor specific energy range. And that's because you're now trading off working capacity with thermal energy input. So yes, you may obtain very good kind of purity and recovery under these conditions, but you're now paying for that in terms of a much higher input energy requirement. This is the same thing for the cement scenario. I'm not going to spend too much time on it, except to point out a couple of things, which are the good ranges, the better performing ranges are much larger, but that's just due to the CO2 content of the stream. But there's an interesting result in the recovery situation, in the recovery data, where there is a region here with high nitrogen loading where the recovery suddenly drops off. And that seems to be due to a greater feed gas requirement. So when you're adsorbing a lot of nitrogen, you also need to feed in, per cycle, you'll feed in more gas to adsorb that nitrogen. So although the CO2 working capacity or CO2 recovery is staying the same, because this is relative to the total feed, you will most likely see a drop-off as you head up in nitrogen capacity. To give you a kind of point of reference, MG 74, which was one of the better performing adsorbents from earlier, is kind of located right at this. I'm not sure if you can see my mouse cursor or the laser pointer, but at this point here. So to then go from there, the question is, well, out of those maps, which areas achieve the 95% purity and 90% recovery target? And that's this cross-section here. So although a lot of the areas are good performing, the best performing areas are a limited subset. I understand that these numbers are a bit meaningless without showing the isotherms, but it highlights that adsorbent design or properties could be helpful in achieving these adsorption properties. But on the next slide is where kind of the interesting results are, is when we compare it to PVSA, so the previous work. The color scales are the same. The top two plots are for PVSA and the lower two plots are for the TSA work. So purity here on the left-hand side and recovery here on the right-hand side. As I mentioned earlier, because we have that extra freedom in the TSA case to supply thermal energy, we lose all of these trade-offs that we previously had for the PVSA case. And the reason why you see those in the PVSA case is if your heat of adsorption is very high for PVSA and you apply vacuum and desorb the gas, you cool the bed too much and your working capacity suffers. So this kind of highlights that you have a wider kind of degree of freedom or wider range of useful materials to employ in TVSA or TSA. I'm going to briefly touch on process economics, and by that I'm just going to speak about it. This is currently still in progress, so I don't have any useful results to show you. But we will be employing indirect heat transfer to heat the bed. This is possibly contentious. Direct heat transfer is, as in using a hot gas to regenerate the bed, is traditionally the method used for TSA. But that is also because the traditional applications of TSA have usually been dehydration. So you use the hot gas to desorb the water, and you don't really mind what happens to that product gas. But in the case of kind of CCS applications or gas separation applications where you want to maintain product purity, you either have to use something like steam regeneration and then condense the steam, or indirect heat transfer. In the case of steam regeneration, there aren't too many studies available yet to show that that is a good idea. Most of the computational studies assume that the steam does not condense and does not fill the pores. But that is yet to be demonstrated. I know that a few DAC companies are employing steam regeneration, but kind of what impacts that has on the adsorbent and on the mass transfer is yet to be established. So we've gone for indirect heat transfer because that means we can have the adsorbent in heat exchanger tubes and have a hot fluid on the outside and the shell side to heat, and then we can run a coolant also on the shell side to cool the bed, to help the cooling of the bed. What this then leads to is a coupled design of adsorber and heat exchanger, because you need to match the kind of adsorbent amount requirements, pressure drop characteristics, flow per adsorption vessel, with the then heat exchange area you obtain and whether that can achieve the heat transfer you need to achieve for your cycle. So this combination, or this coupling, limits your freedom as to the size and number of adsorption vessels. If you need to transfer a certain amount of thermal energy, then you need to have the corresponding heat transfer area. And this is where the major limitation of TSA really comes in, and that's the cooling time. Packed bed style TSA has very poor heat transfer, and that's due to the heat transfer in the adsorbent, so in the bed. And this really results in a very long cooling time. So although you can get excellent working capacity, so in the 2, 3, 4, 5 moles per kilogram range, the productivity becomes extremely low. And the productivity is the amount of product you obtain per unit time, per mass of adsorbent. So although 1 kilogram of adsorbent can capture a lot of CO2, it takes a very long time to obtain that CO2. And this is where I think non-packed bed processes, so kind of rotary adsorbers, monolithic adsorbers, could help with that, improving the productivity. So just a quick summary or a quick conclusion. So we looked at 25 adsorbents, and we have seen much more promising results in terms of CO2 purity and recovery for TSA compared to PVSA. However, the main conclusion is going to come once the process economics are finalized, because that's where we see the impact of the time and the trade-off between the working capacity and the productivity. And although TSA may be better from a pure adsorption modeling perspective, overall, initially at least, it does not seem to be as good as PVSA on a kind of footprint and economic basis. So the next kind of steps are to finalize the process design model to kind of wrap up this work. And then from there, look at rapid cycles, so ways to improve the productivity, and that may come from non-packed bed processes. In the end, or at some point in the future, it would also be nice to include gas impurities and the costs of pre-treatment, but I don't believe we're at a position yet to worry about those details, in great detail. We have a couple of other issues specifically around the productivity to deal with first. So with that, I'd like to thank the Petit and McDowell groups at Imperial for their support and general friendliness. And with that, thanks for your time and happy to answer any questions.
There you go. I finally worked out how to unmute myself and put the things on. So I'd like to open the floor to people to ask questions. And Marco, feel free to unmute yourself, just say where you're from and ask a question.
Yeah, thanks. And thanks, David. I always learn something when you speak.
Thank you.
From the materials chemistry perspective. So, this is very interesting. The comparison, especially between TSA and PVSA. Now, you were mentioning something about steam as a way of desorbing. When we talk about MOFs and we think about steam, that is basically water at very high temperature, yeah. I see two potential problems. One is that the MOF just crumbles. The second, even if the MOF survives, is that probably water will displace CO2.
Everything else.
And then, might displace CO2, which is what you want, but then you have to remove water from your adsorbent, which takes additional energy. So what's your take on that?
Yeah, exactly. You're right. I have nothing further to add to that. This is where kind of a water tolerant MOF is compulsory, right? If you want to use steam. The problem, though, with most of the water tolerant MOFs as well is that they tend to have a low CO2 enthalpy of adsorption, right? So that's really the balance with every adsorbent, not just MOFs. So even if you look at zeolites, which are water tolerant, high silica zeolites, very poor CO2 adsorption capacity. So MOFs for steam regeneration may not be a good idea, but that's where indirect heat transfer might help you. Like it doesn't need to contact the water.
Oh, okay. So yeah, you use it as just as a way of
heating medium.
Something else.
Yeah.
And then you were talking about the issues with heat transfer across the bed. Now, is this something that is, so imagine we have a packed bed with like pellets or beads. Is the problem intrinsic to the pellet or is it extrinsic? So, the problem is the poor thermal conductivity of the MOF, or is it simply that when you have two pellets coming into contact, they don't transfer heat to each other?
Right. Combination of everything. So the thermal conductivity of the adsorbents from the data we have found, which is only for MOF5, 13X, and activated carbon, is quite poor.
Okay.
The good news, though, is the MOFs seem to be higher than zeolites. Right. So in general, we can say that. The heat transfer model that we're using for the bed includes the thermal conductivity in the particle, between particles, so when they touch, and also any convection due to temperature within the free space. and also radiation between the particles. You can improve the heat transfer significantly if you put gas flow through the bed while you're doing the heating. The problem then becomes you are now diluting your product. So you need to...
What if you use CO2 to do that?
Yeah, so the option is to use hot gas regeneration, hot product gas regeneration. You need to then think about, yes, you can do that. That is the best option that you have aside from indirect heat transfer. Once you're cooling the bed, though, you need to stop the gas flow, otherwise you'll saturate your adsorbent with CO2. Yeah. So you need to think about something for the cooling side. That's the only disadvantage there.
Great,
right.
Thanks a lot.
Excellent, thank you very much for that, Marco. Have we got any other questions?
Yeah, there are quite a few in the chat window. Oh, there's one more in the chat window.
There we go, chat window. Why don't you include LDH as a possible adsorbent? Bit high temperature, isn't it? Also,
there are a few.
Chemie doesn't work in LDH.
I mean, I work on all adsorbents, so I don't mind. Just data availability, right? So there are some LDHs and some mixed metal oxides, which we could easily adsorb, you know, around the 40, 50, 60 degrees C area. Not enough isotherms. That's the summary for CO2 and nitrogen.
Okay. Any other questions from any other people?
Yeah, one from me, if you can hear me. It's Greg Much from Newcastle.
We can hear you.
Hi, Greg. Yeah.
Thank you for the talk. Really great talk. As someone said earlier, learned a lot. It was kind of a question, you've just touched on it, about isotherm measurements. So you gave some tips, if you like, to experimentalists about, you know, recording at least 3 at different temperatures, et cetera, et cetera. One thing that you didn't mention that I've come across quite a lot is the effect of pre-treatment. Mm-hmm. So all the data that you're getting from the literature
is excellent regeneration, right?
Yeah, exactly. So
yeah.
Do they pre-treat in the same way for the same amount of time, using a vacuum, same temperature, because it totally changes the properties of the sorbent, right?
Yeah. Yeah, so you're correct. That is something that's out of our control. But no, nobody uses the same regeneration conditions. And some of these adsorbents here, especially the ones that are water sensitive, are extremely sensitive to regeneration conditions, especially things like HCUST1. There are, I would say, papers out there with 2 to 3 times capacity variation between them due to this problem. So no. And also in reality, when you're operating the cycle, you'll never reach the same excellent regeneration as the isotherms were measured at.
Yeah, I guess that's what I was thinking of. I'm thinking of calcium oxide, because I guess if you sinter the hell out of it, you can clean it nicely, but you lower the surface area, so it just changes completely depending on how you pre-treat it. So I guess it's just a limitation of the literature. And again, yeah, like you say, very useful tips of what people should do, but I guess pre-treatment is something in my mind that, you know, if there was a standard procedure or something, might help people like you.
So I think in the case of calcium oxide, it's a physical morphological change that comes from the sintering. If you were to use it in a packed bed anyway, and you'd get terrible pressure drop over time. But in the MOF case, every MOF has kind of a maximum temperature that you can regenerate it at, right? So you're also limited by that maximum temperature. So in general, for zeolites, we would say, regenerate at 350 degrees C under vacuum for at least 12 hours, right? But many MOFs won't withstand those conditions. So that's also another reason why everyone has variable regeneration conditions. But yeah, I agree.
Yeah, okay, thank you very much.
Okay, excellent. Am I still muted? No, I'm not. Excellent, and excellent to bring in calcium oxide as a potential sorbent. calcium oxide for the win. Just saying that, you know, even when it's
No bias whatsoever.
even when it's sintered, it'll still take up quite a lot of CO2, a couple of moles per kilogram. I'm going to ask some mean questions now, because I am a big mean man. So indirect heat transfer is very challenging in terms of exergy destruction, right? Have you done some basic analyses? You could do some order of magnitude stuff without even knowing anything about the bed, because you know what the temperature.
You know the
gradient
temperatures.
You know the temperatures. You can just work out how much exergy you're destroying. Have you done it?
We have not done it. No.
Do it.
We will do it. It's a good thing to include.
I also had how do they stand up to water, which is, you know, another mean, which has been asked before. And finally, the meanest question of all: if zeolites work quite well, why use MOFs at all? Can you give me a rough cost of a zeolite and a MOF?
Yep. So zeolite 13X, let's say bulk unnamed vendor price would be somewhere around 50 cents to $1 per kilogram, up to, if you want the best quality, you know, UOP, top of the range, $5 per kilogram.
I'm all right with the cheap stuff.
So, but the expensive ones are actually significantly better in terms of adsorption capacity. But let's say anywhere from $3 to $5 per kilogram for the good stuff. MOFs, on the other hand, we haven't, you know, I don't know if it's possible to tell you a price because nobody makes them at this scale, right? So if we were, you know, you can do some extrapolation and say, well, if we can achieve the same cost reduction from lab scale to bulk scale as you can for a zeolite, and just apply that same factor to a MOF, which is a bit questionable, but let's say you did that, you're still in the hundreds of dollars per kilogram range.
Okay.
Yeah, that was the cost question. Oh, why do people use MOFs?
Yes.
Because zeolites have been around in the research literature since the 1950s, and people were a bit bored of them.
Yeah, and I guess that's people have been absorbing CO2 with calcium oxide for a while as well. You'll note that I don't really work on that anymore.
No.
Anyway, having said all that,
but also having said, you know, zeolite 13X still sensitive to water, right? If you adsorb water on there, it's a real pain to get it off. So that's the main disadvantage, right? So you still need to do pre-drying with alumina or something like that.
Okay, from 87804671311. Nice to see you there, 87804671311. We're using this particular LDHs, and they're excellent. Well, that's nice to hear. Right.
I ask another question.
Yes. Well, hang on, Marco. Let's just wait and see if anyone else wants to ask a question first.
There is another question, I see.
Right. Leanne, why don't you ask your question in person if you have a microphone?
Yes, I have a question. Thank you.
Leanne, where are you from?
Sorry. I'm from Harvard University in Edinburgh. Yeah.
Right, go ahead.
Yeah, so thank you for the presentation. It's very interesting. So I was thinking to ask, because it seems like in the beginning of your presentation, you mentioned that the screening was very rely on the adsorption isotope measure in the literature. But then from my experience, the measurement of adsorbent isotope can be very time consuming. So my question is, if you would be looking for other kind of metrics to rank this adsorbent in the future, and specifically for the TVSA?
Yep. Thank you for your question. So since we published the work on PVSA, kind of Randy Snur, Arvind Rajendran, and maybe Beren Schmidt, I can't remember, but they've all published similar screening papers using computationally simulated isotherms. Right, so that is also an avenue that you can go down. So you can simulate your 6 isotherms and then run the screening model. That's a perfectly valid option as well if you have reasonable trust in your simulation. But I think the second part of your question about other metrics, so the traditional metrics of like amount of CO2 adsorbed or ideal selectivity or IAST or any of those kind of long-standing metrics. There are quite a few papers out now, including ours, where those metrics basically cannot predict the same order as a simple model like this. So the simple models, although their absolute accuracy is not very high, they can still give you a reasonably correct ranking of adsorbents. So my direct answer would be no, I will probably not look at other metrics just because they're not that good at predicting the final outcome.
Okay, that's
Sorry.
yeah, that makes sense. Yes.
Super duper. Okay, do we have any other questions? What time are we here till, Caris? I think we're supposed to be here till, I think we have a little bit more time, but we might be coming to the end.
Well, it's until 4 o'clock, but if people want to ask questions and David's happy.
Yeah.
For more.
Yeah, I don't mind.
Does anyone want to ask any more questions? I can start bringing out more questions from the big book of meanness.
Can I go with my question?
Yeah, go for it, Marco.
Thanks. By the way, I'm from the University of Pisa in Italy. I forgot to say that. Sorry. Now, my question is, I've seen recently a paper came out where they find out that once a moth absorbs a gas, its thermal conductivity goes down. Now, what is the impact of that on both TSA and PVSA scenario?
For TSA, it would be bad, right? Because at the moment we're using the kind of clean thermal conductivity value, so no gas adsorbed. And it's already really bad. So, you know, once you account for that, it would be even worse. For PVSA, the cooling effect, okay, let's go back to the start. For PVSA, you assume your bed is adiabatic, right? Because the diameter is large, the heat doesn't transfer that easily from the center out to the wall. And any cooling that happens from the desorption is kind of local in your adsorbent particle anyway, as in it's a bulk cooling effect. So the fact that the heat transfer has become worse doesn't really impact the PSA desorption step that much. What it would affect is the thermal gradient as you are feeding the gas in, right? Because a phenomenon you get with any of these adsorption processes is as you feed from whichever direction of the bed, it adsorbs in that kind of layer, and then the heat released from that section is carried with the gas and thermal conductivity up the bed. So if the thermal conductivity was reduced, then it would be beneficial for that scenario. You would actually get more adsorption, greater amounts adsorbed.
Okay. Cool, thanks.
Nice.
Right. Well, thank you very much to David for such an interesting talk. I learned a lot about MOFs, and one thing I was going to say is, have you actually looked at rerun any of these for air capture? That would be interesting.
I mean, the short answer is yes. The long answer is the model isn't really suitable for that, because you really need steam regeneration in the direct air capture case, or indirect heat transfer. But yes, we have. The results aren't very good, but that's more attributed to the model cycle rather than the performance of those adsorbents for DAC.
I'm not against DAC, Salman. I'm, just pro making sure that any analysis looks into it, warts and all. Which sometimes means that I'm anti-DAC. I've got to say, when we looked at some of the MOFs, when Grazia looked at some of the MOFs, we found exactly the same. They just didn't have enough uptake of the load, and so we were making a huge swing in terms of everything else was making a huge cost. Oh well, it's good to know that you also found exactly the same. I mean, the other thing with DAC, the water, right? You're not going to dehydrate air to then put into your DAC. So you really need something that's not going to. Yeah, I mean, I think that you would, you might, depending on where you're actually sitting. I mean, the one thing about air capture is you can site it anywhere. Yes. So if you site it in the middle of Death Valley or something, yes, the relative humidity is low, but there's another problem. The ambient temperature is high. No, that cancels each other out, right? So relative, because for adsorption anyway, the temperature. But the thing with adsorption processes and water is that if you don't, let's say it does adsorb a small amount, and that small amount is now adsorbed, if you don't regenerate it properly, that water is just going to propagate through the rest of the bed, and then you'll just kill your CO2 capacity over time. So although the first week it might be looking good, but in 3 months' time, you'll probably end up with no CO2 adsorption. Sad. Right. Unless Caris has any notifications she needs to do or things to say to people, she probably wants to say, hey guys, come along next week to the next thrilling installment of CCS studies.
It's falling on me to make that announcement.
Apologies,
today,
Rachel.
No, fine. So I'll probably mumble through this. But next week we have on Thursday at 3 till 4, which is our regular slot. We've got Professor Colin Snape, Director of EPSRC Centre of Doctoral Training in CCS and Cleaner Fossil Energy, University of Nottingham, and he will be talking about adsorbents for CO2 capture, challenges and the pitfalls. So again, that's next week, Thursday, 22nd of October, 3 till 4. And yeah, so that's that. And the only other thing for me to say is thank you to you both. Thank you, Paul, and thank you, David. And thank you everyone on the call for your very interesting questions. Caris, is there anything else left to say?
No, I think you've covered it all.
I think that's everything.
Yeah, thank you everyone. Yeah, thank you, David. That was great. It was like really interesting to hear about all your research that's going on there. So it was really good. Thank you.
No worries. Thank you.
And always entertaining, Paul.
Right. Thanks everyone. Bye bye.
Bye bye.
Thanks a lot. Bye bye.